Hello, my name is Mario.cypko from the Digital Patient Modeling Group at ICCAS, the Innovation Center Computer Assisted Surgery. ICCAS was launched in 2005 by the medical faculty of the University of Leipzig. In a cooperation with the University Hospital of Leipzig, we're working on patient-specific models to support physicians in complex decision-making. Our focus now is the treatment of laryngeal cancer. What makes decision-making so difficult? What are our solutions? And how does it work? This and more I will explain you in the next couple of minutes. It might look magical, but it's not magic. A tumor board at the University Hospital Leipzig is a meeting held by physicians from different departments to find together the best therapy for a specific patient. Based on patient-specific information, each physician builds a model of the patient. In this intuitive process, the most important data get connected and are ranked according to different criteria. Due to the different knowledge background and experience of the physicians and the increasing amount of patient data, each of those mental models looks different. This makes a unanimous decision difficult, if not impossible. So the best treatment for each patient cannot always be guaranteed. As in many other areas, computer systems should be used to help doctors make complex decisions and to handle ever-growing amounts of data. All of this serves to guarantee that our patients receive the best treatment options possible. Here at ICCAS, Matthäus Stöhr, our ENT physician, and I, a computer scientist, have been working closely together nearly every day for almost a year to collect all the necessary data and comprehend the relevance and direct causalities. Finally, a probabilistic graphical model will be used to simulate the complexity of decision-making, which is also known as a multi-entity-based network. Let me show you something about it. The multi-entity-based network can be divided into three layers: a model layer in the middle, an inference layer at the bottom, and a visual layer at the top. The core of the network is the model layer. Let me give you a simple example of this layout: the diagnosis of laryngeal cancer. First, we collect all necessary information entities. The more entities we collect, the more complex our network will be, but the more accurate the results will be. Nodes will then be connected by directed edges according to their relationship with each other. Next, the collected information entities have to be categorized according to the information they may represent. To make this example as simple as possible, nodes are only assigned binary values. We also need to employ conditional probability tables. These tables contain probabilities for certain events, each depending on all possible combinations of its directly causal events. The more detailed these categorizations are, and the more direct causal they are, the more extensive the probability tables get. Also, we need to collect data on patients at different points in time for similar information entities. But there is no way to know in advance how many of those entities will be needed. So the network is constructed as a first-order logic model, which means that arguments need to be added to any information entity, so that any entities and even whole subgraphs can be repeated any number of times. Finally, depending on the provided patient data, we get a patient-specific Bayesian network. On the inference layer, we're calculating probabilities for information entities we are interested in, but that are still unknown. This is done on the basis of the patient data input, shown in red, as well as the conditional probability tables and complex algorithms. Here, we are working to enable the computation of extreme large models in what we hope is approaching real time. On the visualization layer, we are trying out different approaches to make the model as easily comprehensible as possible for both doctors and patients. You can either use the model's inherent graph structure, or you can work with diagrams, simple lists, or more futuristic tools. At this early stage, our model contains over 600 information entities connected by over 800 directed edges. During our research on the model and inference layer, we can already use the visualization layer for medical education and communication between experts or with patients. I believe in the future, such a support system based on a multi-entity-based network not only will propose decisions, but give to the physician a number of its most significant influences. There's a lot to do, but we're looking forward to the day when every single patient will be treated according to the best available knowledge from around the world. Thank you for your attention, see you next time.